usually when we talk about a medical diagnosis, there's this expectation of engineering level precision, you
Yeah,
know? Like
absolutely.
you break your arm, the x-ray shows that jagged white line, and the doctor just points and says, there it is.
Broken or not broken.
Yeah.
It's clean. It's completely binary.
Exactly. It's clean. But the moment you zoom out from that localized bone fracture and try to figure out how a sprawling hospital system actually achieves, say, 0 patient falls over a 3-year period.
Yeah, that clean X-ray machine kind of shatters.
It totally does. And honestly, you face the exact same murky landscape just trying to figure out why your Friday night pizza delivery arrived cold.
Oh, for sure.
And the secret to both of those scenarios, the hospital's triumph and the pizzeria's failure, it lies entirely in how human beings define and measure the concept of quality.
Yeah, and that's exactly what we're getting into today. Welcome to this deep dive.
We're dissecting the hidden science of quality control today, right?
We are. We've got this fascinating stack of data we're looking at, ranging from comprehensive textbooks on measuring and controlling quality to specialized presentation decks on measurement system analysis.
Yeah, down to the actual statistical guides used by software like Minitab to run gauge R&R studies.
Right. And our mission today is to unpack the invisible systems that ensure the things you buy and the services you rely on actually work.
We really want to give you, the listener, a framework for measuring success in your own complex projects. But, to even begin measuring perfection, we first have to define what perfection actually looks like.
Yeah, and defining a perfect physical object on a factory floor is a completely different universe from defining a perfect human interaction in, like, the service industry.
Oh, the contrast is staggering.
It really is. Because manufacturing quality is inherently tangible. Costco is a prime example from the literature we looked at.
Right, Costco.
Their merchandise executives view their biggest existential threat as simply failing to deliver the exact quality they promise.
They don't just rely on gut feelings for that, do they?
No, not at all. They implement these stringent physical processes, like they are measuring the exact micrometer size of cashews.
Wow.
Yeah, they measure the precise amount of skin left on canned peaches.
Wait, measuring the skin on a peach? That sounds almost absurdly obsessive.
That sounds crazy, right? But when you think about the scale of a company like Costco, that tiny variance in texture ruins the perceived value of the products.
Oh, I guess that makes sense. If a customer bites into a tough piece of peach skin, that brand trust erodes instantly.
Exactly. And it goes well beyond just sensory experience into actual safety.
Like with the ground beef.
Right. To prevent E. coli outbreaks, Costco actually bypassed standard suppliers, built their own processing plant, and they test the meat every 15 minutes.
Every 15 minutes? That's intense.
It is. It's a continuous physical check.
Yeah.
Or look at Mesa Products. They're a manufacturer of magnesium anodes used to control pipeline corrosion.
Right. We read about them. They were consistently missing their target of shipping products within 3 days, right?
Yeah. And their solution wasn't some complex algorithm. They just built a 5,000 square foot covered storage area.
So simple.
Right. By protecting their inventory from the weather, their on-time shipping jumped from 93% to 97%.
That's huge. The physical environment literally dictated the quality metric.
Exactly.
But the second you pivot to the service industry, all that comfortable tangibility just vanishes. If you manufacture a defective magnesium anode, your inspector finds it and throws it in a scrap bin before it ever leaves the building.
Right.
But in the service sector, there is no scrap bin.
No, there isn't. The service is produced and consumed simultaneously. Quality professionals actually refer to that as an external failure.
An external failure? So, like, if a waiter is rude to a customer or a nurse ignores a call button, that error reaches the consumer the exact millisecond it is created.
Exactly. There's no quality control inspector hiding in the kitchen who can intercept a waiter's bad attitude and throw it in the trash before it hits your table.
Which means the only way to control quality in a service environment is to translate subjective human feelings into strict, measurable rules.
Yeah, you have to. You
Yeah.
could just tell your hotel staff, be courteous.
Right, because courteous to me might mean a friendly chat, while courteous to you might mean leaving you completely alone.
Exactly. The sources call these operational definitions.
Yeah.
You have to define courtesy as something painfully specific,
Like what?
like addressing the customer as Mr. or Ms.
Uh-huh.
within 5 seconds of them walking through the lobby doors.
Okay, I get it. It's like the difference between inspecting a circuit board and inspecting a hotel room.
That's a good way to look at it.
With the circuit board, you have a physical measurement. copper plating thickness or drilled hole locations. But with
Right.
the hotel room, your yardstick is a 12-point checklist looking for subjective things like shampoo bottles on sink or bed properly made.
Yeah.
One is a physical law, the other is an agreed upon standard.
Right. And that operational definition is the only way to make a subjective feeling countable. Take the pizza delivery fulfillment process, for example.
Okay.
The quality metrics tracked by major chains aren't just a taste test of the pepperoni. They track the percentage of calls placed on hold.
Oh, interesting.
They measure the exact accuracy of the ordered ticket sent to the kitchen. Because, the quality of the pizza itself becomes entirely irrelevant if the customer has already been sitting on hold for 10 minutes before they even get to place the order.
Yeah, I'd be furious before the pizza even went in the oven. Every single touch point is a potential failure point.
Exactly. And the stakes scale up dramatically when you apply those same operational definitions to healthcare.
Right, the sources highlighted Adventist Health Castle, a hospital system in Hawaii.
Yes, they adopted a chasing zero harm philosophy.
And they managed to achieve zero CAUTI, which is catheter-associated urinary tract infections, in their inpatient units for over 3 years.
3 whole years.
Yeah, and they didn't do this by just asking nurses to be more careful. They built systematic accountability, where everyone, from the CEO down to frontline directors, is continuously measured on 90-day action items.
They essentially force human care processes to be monitored with the same rigorous mathematical exactness as an assembly line.
It's fascinating. But because a hospital visit is so different from a canned peach, the actual math used to count the mistakes has to change, right?
Oh, absolutely. Translating a hospital visit or a pizza delivery into the same mathematical universe as a canned peach forces organizations to make strategic choices about the very nature of the data they collect.
Okay, so let's get into the types of data.
Data and quality control generally falls into 2 distinct buckets. You've got attribute measurement and variable measurement.
Right, attribute measurement is just the presence or absence of a nonconformance, right?
Yes.
Yeah.
Did the IV fluid run out? Yes or no? Is the shampoo bottle on the hotel sink? Yes or no?
Checking a yes or no box is cheap and incredibly easy for employees to execute.
It is, but statistically, it's a really blunt instrument.
How so?
Well, if an organization relies purely on attribute data, they're forced to use massive sample sizes just to get a signal through the noise. It tells you a failure happened, but it gives you zero depth on how close you were to succeeding.
Ah, got it. So variable measurement solves that depth problem.
Exactly. It's data collected on a continuous scale. Length, weight, exact time, exact temperature.
So instead of asking, did the pizza arrive late, you measure the pizza arrived in exactly 34.2 minutes.
Precisely. Variable data is statistically far more powerful and requires much smaller sample sizes to spot a trend.
But I'm guessing it's more expensive.
Oh, infinitely more expensive and time-consuming to collect.
And even when you collect all that precise data, you run into the reality that not all errors carry the same weight. Like a pizza taking an extra 5 minutes to arrive is annoying,
Sure.
but a hospital administering the wrong dosage of medication is catastrophic.
Right, which is why organizations have to build composite indexes to reflect the actual damage and error causes. FedEx handles this brilliantly, actually.
Oh yeah, with their SUQI dashboard.
Right, their service quality indicator. It's not just a flat list of mistakes. It's a weighted algorithm.
How does the weighting work?
Delivering a package on the right day, but past the promised time, is a minor inconvenience, so it gets a weight of 1.
Okay.
But losing a package entirely or destroying the contents? That destroys customer trust irreparably, so it gets a massive weight of 10.
Wow, a 10.
Yeah. This index forces the entire corporate structure to focus their resources on the failures that actually threaten the business, rather than just the minor errors that happen most frequently.
That makes a ton of sense. And this weighting concept is also how you compare quality across wildly asymmetrical scenarios, right?
Definitely. Think about an airline handling baggage. One passenger walks onto the plane with a single backpack. The family of 6 behind them checks 8 massive suitcases, 2 strollers, and a set of golf clubs.
Right. If the airline just measures lost bags per customer, the data is horribly skewed against the family.
Exactly. To standardize that chaos, the industry uses metrics like DPMO.
Which stands for defects per million opportunities.
Right. And EPMO, errors per million opportunities. It reorients the math around the complexity of the task. That family with a massive luggage haul represents 11 distinct opportunities for an error to occur.
While the single traveler represents 1 opportunity.
Exactly. By dividing the total number of actual errors by the total number of opportunities and then multiplying by 1 million, you generate a standardized score.
So, a global airline can now fairly track their baggage handling performance across totally different airports, seasons, and customer profiles.
Exactly right.
Now, all of this complex math, these massive composite indexes, it ultimately serves one central economic reality, doesn't it?
It does, the cost of quality.
Right, the cost of quality. The literature estimates that 60 to 90% of total quality costs stem purely from internal and external failures.
Yeah, it's a huge chunk.
I really want to linger on the rule of tens here because it paints such a vivid, painful picture of how bad quality compounds.
Oh, the compounding cost is brutal. Imagine a manufacturer designing a new electronic component.
Okay.
If an engineer spots a flaw during the initial design phase and changes the blueprint, it might cost 50 cents in labor to fix.
Just 50 cents.
Right, if they miss it and a worker has to test the physical component on the line, that test costs $5.
Okay, jumping up.
If the test fails and they have to replace the part during assembly, which is an internal failure, it costs $50.
Ouch.
But if that defective component actually leaves the factory, reaches the consumer, and fails out in the field,
That's the external failure.
yes. And you are paying for shipping, customer service, warranty replacement, and reputational damage. That external failure costs $500.
Wow. So a 50-cent problem ignored becomes a $500 catastrophe.
Exactly. The ROI of prevention is just massive.
The financial incentive to catch errors early is totally undeniable. But I mean, this obsession with metrics can easily backfire.
Oh, for sure.
Let's go back to that Domino's pizza delivery example from the early days of the fast food pizza wars.
Right, the 30 minutes or less guarantee.
Yeah. If leadership simply mandates the metric average daily time to delivery must be under 30 minutes, they might achieve that number, but they incentivize disastrous behavior.
Yeah, you might get a perfectly fast delivery, but a driver who is speeding, running red lights, and causing accidents.
Exactly. So they look great on the dashboard, but the metric itself becomes a hazard because it was divorced from the broader goal of safety and quality.
You get exactly what you measure. If your operational definition is too narrow, employees will ruthlessly optimize for that specific metric, even if it burns down the rest of the business.
Right.
But that behavioral loophole leads us to an even more fundamental, terrifying question about quality control. We've established why metrics matter, but all of this assumes the data we are plugging into our FedEx CQI dashboards and our DPMO formulas is actually true.
Yeah, what happens when the yardstick itself is lying?
Exactly.
Because if we are betting the company's reputation on preventing that $500 field failure or relying on data to keep patients safe in a hospital bed,
The stakes are incredibly high.
they are. And the terrifying reality is that the data we look at isn't objective reality. It is reality filtered through the flaws of our measuring tools.
The statistical term for this is the total variation equation.
Let's break that down.
Sure. The total observed variation you see on a spreadsheet is the sum of two distinct things: the true physical variation of the product plus the hidden variation introduced by the measurement system itself.
And the science of controlling that hidden variation is called metrology.
Yes, metrology. It encompasses the people, the equipment, and the procedures used to assure the correctness of a measurement. And frankly, human beings are incredibly bad at metrology.
Yeah, the sources show that inspectors relying purely on manual visual inspections have error rates ranging from 10 to 50%.
Which is wild.
I mean, flipping a coin gives you better odds than a fatigued inspector on a fast-moving assembly line.
It really does. And the speed of inspection certainly degrades human performance, as does the complexity of the part. But the most dangerous, counterintuitive factor in human inspection is actually a low defect rate.
Wait, a low defect rate is dangerous?
Yeah, it's wild. When a factory gets really good at producing quality parts, the visual inspector gets complacent. Their brain's predictive processing takes over.
Oh, I see.
Because they expect every part coming down the line to be perfect, their optical cortex literally stops registering the rare defect when it passes right in front of their eyes.
That is fascinating and terrifying. So the human element is flawed, but the physical tools fail just as spectacularly.
Oh, absolutely.
Imagine an inspector using a micrometer to measure the thickness of a steel component, but the tool hasn't been calibrated and is reading 0.0002 inches too low.
That microscopic bias causes a dual economic hit.
How so?
First, perfect parts that are sitting right on the lower edge of the acceptable tolerance are suddenly measured as too small, so the company throws perfectly good money into the scrap heap. Simultaneously, defective parts that are actually too big are measured as acceptable and shipped to the customer, triggering that $500 external failure cost.
Just chaos. Total chaos from an uncalibrated tool. So to prevent that chaos, organizations evaluate their measurement systems based on two foundational pillars: accuracy and precision.
Right. Accuracy is the difference between the true value of a part and the observed average of your measurements.
So it measures systemic bias, like is your tool consistently reading too low?
Exactly. It also measures stability. Does the tool drift as the factory gets hotter throughout the day?
Okay. And precision?
Precision, on the other hand, measures the random variation built into the instrument itself. It's the closeness of repeated measurements to each other, regardless of whether those measurements are actually correct.
Let me use an analogy here to make this stick for you. Think of your bathroom scale.
Okay.
If you step on it 3 times and it says exactly 150 pounds, 150 pounds, and 150 pounds, it is highly precise.
Right, there is no random variation.
Exactly. But if you actually weigh 140 pounds, the scale is completely inaccurate. It has a built-in 10-pound bias. It is consistently precisely wrong.
That's a perfect analogy.
Yeah.
A system can be highly precise without being accurate, and perfectly accurate on average without being precise.
And because the stakes are so high, organizations don't just calibrate their tools and hope for the best, right?
No, they deploy a rigorous statistical stress test called a gauge R&R study to prove mathematically whether their entire measurement ecosystem is trustworthy.
Gauge R&R. Let's break down those two R's. They stand for repeatability and reproducibility, which basically isolate the machine's failure from the human's failure.
Yes. Let's start with repeatability, which is the equipment variation. It asks, if the exact same operator measures the exact same part multiple times with the same tool, do they get the exact same result?
Okay, so that tests the equipment and reproducibility.
That's the appraiser variation. It zooms out and asks, if completely different operators measure the exact same part with the same tool, do they get the same result?
Structuring a test to answer those two questions requires different physical methods, doesn't it?
It does. You use a crossed study when everyone can measure the exact same physical part multiple times without altering it.
Like 3 operators passing a batch of solid steel fuel injectors back and forth.
Exactly, but you have to pivot to a nested study when you are dealing with destructive testing.
Right, because if my quality metric is, say, the breaking point of a steel cable or the tensile strength of paper, the first measurement literally destroys the object.
You can't exactly remeasure a snapped cable.
No, I can't hand a snapped cable to the second operator and ask them to measure when it breaks. I have to assume the batch coming off the line is homogeneous enough and nest those distinct parts within each operator's testing block.
Right. The statistical math has to adapt because the physical reality prevents identical repeatability. But once you run either of these studies, you feed the data into software like Minitab, and it generates ANOVA tables.
Analysis of variance.
Yes. And the sheer genius of ANOVA is how it mathematically isolates the spread of your data. If your repeatability variance is massive, ANOVA proves that your physical tool is imprecise, and you need to invest capital into buying better micrometers.
Okay, so it blames the tool.
Right. But if your reproducibility variance is huge, ANOVA proves your tool is fine. But operator A is squeezing the calipers entirely differently than operator B.
So I had a practical question then. If I run this study on my factory floor or in my hospital ward and my error rate is terrible, I don't just throw all my instruments away.
Not necessarily.
Mm-hmm.
If the ANOVA table points to reproducibility, you don't need to buy new tools. You just need to spend an hour training your operators on a standardized procedure.
That's brilliant. It pinpoints exactly what needs fixing. The software also gives you an expert chart, plotting the average measurements of the different parts.
It does.
And the most counterintuitive thing about a successful gauge R&R study is that you actually want the expert chart to look totally out of control, right?
Yes, you really do. You want the data points breaking through the control limits violently.
Wait, violently breaking out of the limits, why is out of control a good thing here?
Because the control limits on that specific chart represent the background noise of the measurement error. If the measurement system is highly precise and trustworthy, the only major variation it should be detecting is the true physical difference between the distinct parts themselves.
Ah, see.
When the data points bounce wildly outside the limits, it proves your tool is sharp enough to easily distinguish a large part from a small part, rather than being overwhelmed by its own internal static.
That makes perfect sense. So once you have these charts, how do you know if you've actually passed the test?
The Automotive Industry Action Group, the AIAG, sets the gold standard here.
Okay, what are their guidelines?
They look at your measurement system error as a percentage of your total variation. If that error is under 10%, your system is acceptable. You can trust your dashboard.
Under 10 is good. Got it.
If the error is over 30%, your system is totally unacceptable. Your yardstick is lying to you, and any decisions you make based on that data are essentially garbage.
Yikes. Over 30 is terrible. What about in between?
Anything sitting in the 10 to 30% range is a gray area, really dependent on how expensive the tool is to replace and how critical the measurement is to safety.
Wow. We've covered incredible ground today.
We really have.
We started by exploring the fundamental friction between manufacturing and the service industry. You know, how measuring the physical skin on a Costco peach is entirely different from defining the subjective courtesy of a hotel clerk.
Yeah, and we moved through the strategic choices between attribute and variable data and the compounding financial terror of the cost of quality.
And finally, we unpack the deep statistical stress tests, like Gauge R&R and ANOVA, that prove whether our yardsticks are reflecting reality or just amplifying noise.
It's all about making sure the data you're using is actually telling you the truth.
Exactly. So the ultimate takeaway for you listening is to scrutinize your own projects. Are you tracking metrics that actually align with your end goals, or are you just optimizing for a faster pizza delivery at the expense of everything else?
Right. Are you incentivizing the wrong behavior?
Yes. And more crucially, is the system you rely on to gather that data actually trustworthy, or is it just consistently precisely wrong? We've talked extensively about the monumental challenge of using operational definitions to measure human behavior in the service sector. But I want to leave you with one final thought to mull over.
What's that?
Well, as artificial intelligence and machine vision become embedded in our physical spaces, monitoring every micro-expression and second of our workday, what happens when an algorithm begins conducting real-time gauge R&R studies on human empathy?
Oh, wow.
Will we finally perfect the intangibles of the service industry, or will we mathematically optimize away the very humanity that makes an interaction feel authentic in the first place? Suddenly, that clean binary X-ray we all wanted at the very beginning,
Right.
it doesn't seem quite so simple anymore.